So, in the last few lectures we defined the semantics and the syntax and the semantics of first order logic. Let us continue by looking at semantics in a little bit more detail, because first order logic is a language which is the most commonly used language in computer science, and it includes, for example, all the programming languages that you use. They can be modeled in first order logic, and you can see that essentially in a programming language you are dealing with variables and constants and things like that. So, let us just have a closer look at what are we really saying when we use first order logic, and then we will move towards two sides of it. One is how do we say or how do we express what we want to represent, and that is a side of knowledge representation, that if you want to represent knowledge in certain domain, what can you really say and how do you say it, and it is a very vast subject and it has been dealt with by many people in great detail, but we will try to get a general idea of how to use FOL to start with essentially. And then we will move towards a proof system. We will look at how proofs are generated in first order logic, and we will see that essentially they will incorporate some level of search essentially. And then we will come back to knowledge representation and try to really study of how in a real domain we can represent knowledge essentially. Okay. So, let us first begin with an understanding of FOL semantics. So, if you remember, a first order language is a language which is defined by a set of relation symbols, a set of function symbols and a set of constant symbols. And given this alphabet, we had defined a set of terms. So, if you remember, variables are terms or constants are terms, or if you take some function symbol and give it an appropriate number of argument, then they are terms essentially. Now, terms denote elements of D. What is D? D is the domain that we are defining the semantics in terms of. We are saying that there is an interpretation I, interpretation of a set of sentences. So, you are saying some sentences in this language and what do they mean essentially. So, that is one side of semantics as to what does a sentence mean, and the other side is of course, whether those sentences are true or not. And the interpretation in first order logic is always in terms of a domain D and a mapping I essentially. What this mapping I does, if you recall, is that it maps the set R onto relations on D, it maps the set F to functions on D, the set D, and it maps the set C to constants of D. And together with these two, we have the family of terms that we are talking about. So, the thing is that terms always denote elements of the thing. So, this is the first thing that you must sort of get used to, is the idea that the semantics of first order logic is set theoretic essentially. Talking about sets. And what is the set we are talking about? The set that we are talking about is the set D, which we have called the domain. Some books call this the universe of discourse, but it is made up of a set of elements essentially. And essentially what first order logic is talking about are some properties of elements in these sets essentially. So, terms are used to denote elements, that you can say that x is a term which you do not know, which will be given to you by an assignment, or you can say 3 is a element in my set of numbers, or you can say 4 plus 7 is an element in my numbers. or you can say that father of John is a element in my set. So, depending on the domain that you have chosen, terms denote elements essentially, and relations, as we have said, denote or predicates denote relations on D, and the simplest kind of predicates are unary predicates. So, for example, we have already said man x or mortal x. So, when it is unary, it basically means that it takes one argument. We could have said p of x, it does not matter. Just like in computer programming, the name that you give to a variable is immaterial essentially, that it does not carry and have any effect on the computation that you are doing. Likewise, in logic, the name that you give to a variable or the name that you give to a predicate is immaterial essentially. So, what really matters is what are the relations between elements of a set essentially. Now, as you know, unary relations, they correspond to subsets of D essentially. So, how do we visualize these predicates essentially? If we were to draw the set D, then we are saying that there is some subset of this which is the set which is denoted by man essentially. So, this could be man. Okay. So, every unary relation denotes a subset essentially. Now, the first thing to observe here is that in English language we have different kinds of categories of things. So, you may have a taxonomy of life forms in which human beings sit somewhere. You may have properties such as red, green, blue, or the property of being mortal. We do not make this distinction in first order logic. For us, they are just subsets. So, if I say red x, which means that x is red, it does not have the kind of meaning that we use as humans essentially. That is a issue which we will address to a little bit later when we get deeper into knowledge representation. But as far as the current moment is concerned, whether they are categories or whether they are properties, we will denote them with unary relations or predicates of arity 1, and we will just simply think of them as sets essentially. So, thus man is the set of all men, which includes women of course. So, we say, I mean we use that for humans. Mortal is a set of everything that is mortal, red is a set of everything that is red. In fact, this predicates define these properties essentially. Now, you might ask, what do you really understand by the term red essentially? So, if you are a very science kind of a person, you might want to say something like, you know, it is a frequency of light and that is reflected by the object and the kind of reaction it makes into your onto your cornea of your eye, based on which there are some signals which happen and they make you perceive the notion of red. All that is an explanation of what is red essentially. We are not interested here in first order logic on all that kind of stuff. All we are saying is that red is a unary predicate, which means it is a subset of this thing. So, let us look at this statement that we have started working with, which is says that for all x, man x implies mortal x. Yeah, it is a sentence in my first order logic, and it is a sentence which will be true or false essentially depending upon the domain essentially. When will it be true or false? The semantics is defined, as we have said, it is model theoretic semantics. It will be true if you look at it from a set perspective, that essentially we are saying that if x belongs to the set called man, then x must belong to the set called mortal essentially. That is all we are saying in this statement. For all x, if x is a man, then x is mortal essentially, which means if x belongs to man, then S must belong to mortal, which means that my set mortal must be a superset of my set of men essentially. So, this statement is essentially equivalent to saying set of men is a subset of the set of mortal things. Let me just use the word things. Nowadays in ontology, when you talk about a domain, then you say that the topmost level is thing essentially, everything is a thing. So, this is the first thing you must understand in terms of semantics of this first order language, that we are talking about sets and unary relations are denoting subsets of the domain, and logical connectives basically talk about connections between these different sets essentially. So, they are relating two sets, man x and mortal x and so on. Likewise, relations of higher arity denote, or predicates of higher arity denote subsets of cross products of an appropriate size essentially. So, if you say that the relation friend x y, if you say, which is a binary relation, it is basically a subset of D cross D, where the two elements or the pair are present. So, which basically means that if that pair is present in that relation, then the predicate is true essentially. So, that is how the semantics of first order logic is defined. Now, obviously, this can be very restrictive in nature. So, if you want to use first order logic for knowledge representations, there are many things that are difficult to express in first order logic. So, one of the restrictions is that when you look at a predicate, take terms so, that is the first thing you must realize, that predicates take terms as arguments. So, whenever you have a predicate, so for example, if you have p of x y z, then x y z can only be terms essentially. What is the implication of this? That you cannot, how do you express something like this? Okay. This is an example which I have taken from this book by Charniak and McDermott, one of the popular books on AI, and they have a nice section on logic and deduction, which I would encourage you to read essentially. How do you express something like John believes that the earth is flat essentially? Now, our natural tendency would be to say that there is a predicate for the word believes, and the arguments to that predicate could be who believes what, for example. So, you might want to say something like John, but what does he believe essentially? The earth is flat. So, I would write it something like this. I would want, this is what I would want to say essentially, that belief is a relation which captures what John believes in. So, the first argument is the person who believes it, and the second argument is what that person believes. And the second argument is, unfortunately, in this example a formula. And we have said that the semantics of first order logic is that predicates take terms as arguments, and the terms denote elements in the domain essentially. So, essentially first order logic allows you to talk about elements of the domain. What about sentences when we talk about people and things like that, that John knows that Mary did this and that kind of stuff essentially. That is a difficulty with first order logic. We will try to see how to get around this fact. So, there are different approaches. One is that we can try to twist or extend FOL to somehow include formulas as part of the domain. So, that is a process that we will look at later, which is called reification. That we reify those formulas and so when we say that believes John flat earth, we are not really talking about the fact that it is a sentence, but that it is a formula which somehow. So, it is not a very neat way of doing things, but people have tried to get around this sort of thing essentially. So, that is the problem with first order logic. Then how does one reason about time and change? Because when we talk about first order logic, we are saying that you are given a set of sentences, and as a consequence of that set of sentences, certain more sentences are entailed by it essentially. How does one bring time and change into the fact essentially? That is a very difficult kind of a thing. So, you might, somebody might say that today they might say that politics is dirty business, and tomorrow they might go and join some political party. How do you cater to change happening in the real world essentially? Or you might say that I have got a block of ice on my table essentially, and in Chennai of course, that does not stay for very long. So, after some time that statement will not be true essentially. So, in a changing world, how can we reason about a changing world? That is another thing which is a little bit difficult in FOL. The simplest approach that you can think of is that you can include another parameter called time essentially. You can say that this statement is true at this given time essentially, but that also gives rise to, as we will see later, something called the frame problem, which says that if you said that Pythagoras theorem was true at time t1, how do you now make the statement that this theorem is also true at time t2, which happens afterwards essentially. So, in effect everything that was true at a certain time, you would have to now worry about how to assert whether it is true at a later time essentially. So, these kind of difficulties exist essentially. Then how do you reason about continuous things essentially, or at least things that we perceive to be continuous, because we tend to see a lot of things as continuous, though in practice they may or may not be continuous. So, for example, reason about water. So, if you see the kind of statements that we use the term water in, water flows under the bridge, or he drank a glass of water. Now, they have different connotations essentially. When you say water flows under the bridge, you are making some statement about a category of things and things like that essentially, a class of things. And it is not if it is remember that the set theoretic semantics of FOL forces you to talk about elements of the domain and relations between elements of the domain. So, that is about all that you can do. How do we talk about things like water essentially? So, if I say there was water in a glass and he drank half of it essentially, how do we talk about such things essentially? Because when I say there was water in a glass, essentially if I say something like in glass water, So, let us say it basically is it is a predicate between two elements, one is called glass, the other is called water. But is that, does that capture our notion of what we are trying to say? Does it, so these are difficulties. How do we reason about space? So, this notion of in that we have said is basically a spatial notion essentially. So, we can define somehow the semantics of what is it, what does it mean to be in, if we define some axioms for spatial reasoning and so on. But how do you say, for example, that we are all sitting in this room essentially, or if you draw a circle and you say that he is within the circle essentially, or if, how do you distinguish between the fact that a rabbit may have been swallowed by a python, for example, which in which case of course clearly the rabbit is in the python, as opposed to a fact that the python is lying in a circle and the rabbit is somewhere in between essentially. So, do we say that that means that the rabbit is also in the this thing. So, reasoning about time, change, continuous elements is hard in first order logic, but we will gradually try to circumvent these things essentially. Let me come back to the notion of entailment. So, we had defined the notion of entailment. We had said when we were looking at predicate in propositional logic, we had said that a set of sentences entail a formula alpha. Whenever S is true, alpha must be true essentially. So, we carry forward this notion of entailment to FOL, and in FOL we say that a set of sentences S entails an alpha if whenever an interpretation I entails the set S. So, what do we mean by whenever an interpretation I entails a set S? It basically means whenever we have a model for S essentially, which means that we have chosen a domain and an interpretation mapping for the domain. So, whenever the set of sentences S is true in interpretation, then the sentence alpha must also be true in that same interpretation. So, this is how we carry forward the notion of entailment to first order logic. We are saying that in if S has a model, then alpha must be true in that model essentially. So, that is the notion of our entailment. Now, let us say we define, just to distinguish between the syntax and the semantics part of it. Let us say we define a simple language in which R has two relations, let us say G and let us say T, it does not matter, and the set F has also two relations, let us call it S and C, and the set C has one symbol, let us just call it Z essentially. So, once I have defined these three sets, the set of relation symbols, the set of function symbols and the set of constant symbols, and of course, I have the set of variables, I can always write formulas. Now, I can say for example, G, assuming that it is of arity 2 of C, sorry not C, X and S of Z. I can make statements like this, and these are formulas in my language. If I make sure that there are no free variables. So, for example, if I say that for all x this is true, then I have a sentence in my language essentially. So, I can of course define a language given having chosen this vocabulary, but what about the meaning of these sentences essentially? We have said that the meaning is given by a model essentially. So, I just want to illustrate the fact that by choosing different models, you may have different meaning for the same set of sentences essentially. So, what could be the two different models? So, let me rub this off, and let us say one model we call as a Z model, and in that model let us say d is equal to integers. So, I am talking about the domain of integers. Then I say that G belongs to or refers to greater than, and T refers to some relation. Okay. So, let us say T refers to something, let us say less than, it does not matter essentially. Because I am talking about integers, the notion of less than and greater than is defined on those integers. So, whenever I use the formula G of some two terms, I am essentially saying the first term is greater than the second term essentially, or some whatever my meaning of the thing is. And I could say that S is a successor which is equivalent to saying that plus 1, and I could say that C stands for plus essentially. So, C is a function and plus is a function of two arguments. So, let us say that this is of arity 2, this is of arity 1, and I could say that Z stands for 0. So, I have defined a language, I have defined a domain of integers, and I can make statements about some number being less than another number or some number being greater than another number, and depending on what statements that I am making, those things may be true or they may be false. So, if I have a set of statements, for example, if I say if my S is a very small set, for example, let us say it contains one statement which says that the successor of Z is greater than Z. Let us say some very small set of statements, only one statement in fact. Now, obviously, for this set S, my domain D of integers is a model essentially, because all I am saying is that I need some domain in which the greater than relation which I am saying holds between the first argument and the second argument, and the first argument is the successor of the second argument essentially, which is true in integers essentially. So, in integers this formula is true. So, therefore, this domain is a model for this set of formulas. You can add more formulas about properties of integers and so on. You can define the fact that that addition is commutative, for example, you can define it using these kind of symbols essentially. But I could also choose a different model, strings over the alphabet A, let us say. So, you all have studied formal languages, and I could choose say that I am talking about this thing. Now, what could be the meaning of my relations? So, here G could be, for example, longer than, T could be, let us say, shorter than. At this moment I can't think of a different one, but you can think of anything essentially. The notion of an interpretation is that you are saying what does that relation mean, how does it relate two elements together essentially. S could be a function which also defines a successor, which says that that successor of x is equal to x followed by a. Okay, I could define my notion of a successor like this. C could stand for concatenation, and Z could stand for the empty string essentially, or something like that. So, anyway, the point is not to actually look at these two domains, but the point is to learn to discriminate between the syntax and the semantics. The syntax is defined by an alphabet and the language that we construct over the alphabet. So, in this case there are 2 relation symbols, 2 function symbols and 1 constant symbol, and we can define a whole set of sentences in this. Whether those sentences are true or false is the kind of thing we are interested in. So, if we choose a subset of set of such sentences, and if we can construct a model for it, which means you can find a domain and an interpretation. What is an interpretation? It tells you what is the relations and what are the function and what does the constant refer to, such that the sentence is in the set is true or the theory is true, then we have found a model for that. But a given set of sentences may have more than one model essentially. So, for example, for this very small set of which contains only one sentence, both these interpretations are models essentially, because in both those interpretations, in one case the successor number is always greater than the other number. In this case, if you successor is defined by appending a at the end of it, then it will be longer than the other number essentially. So, this sentence that we have g of s of z comma z is true in both the models. So, both are models of this essentially. So, one of the things that we would be interested in as a knowledge representation exercise is that if we write a set of sentences, which is what we would call as a knowledge base, then is our description enough to assert the fact that the models of that set of sentences is what we intend essentially. In a sense, have we said enough in our theory to demarcate the domain that we want to talk about essentially. Because if that is the case, then we are really talking about a domain essentially. So, you have to say things in precise enough detail and you have to say enough things for your knowledge representation exercise to be meaningful essentially. So, when we work with logic, we work at the syntactic level essentially. Okay. We have seen that proof systems are syntactic in nature, but our goal is obviously semantics. We want to do something meaningful essentially. So, if we want to create a set of sentences, then we want to say enough sentences which are true for a model. So, for example, you must have heard about things like Peano axioms. Which are used to define number systems, or you must have heard about Euclid's axioms about geometry. So, you make a certain set of sentences which are true and which define a model, for which numbers are a model for Peano systems and geometry is a model for Euclid's system and so on essentially. So, the thing that you must remember is that first order logic is talking about sets and relations between sets, and when we write proof systems, we essentially want to write those proof systems where everything that we can prove is happens to be true, which means that our proof system is sound essentially and hopefully complete also essentially. So, in the next class we will start by looking at what are the new rules of inference we need in first order logic, and then we will try to look at one approach to generating proofs essentially.